Welcome back. Our next speaker, Stefano Albrecht, sadly couldn't be here in person, so he's going to be presenting online. Can you hear me, Stefano?
Yes. Hi, everyone.
Excellent. Speaking about learning and collaboration in human AI teams. Please take it away, Stefano.
Okay, first quick check. You can all hear and see me okay?
Yeah, sounds good.
Great. My name is Stefano Albrecht. I'm director of AI at DeepFlow, which is a startup company in London where we are building multi-agent LLM technologies for workspace orchestration. And then with me, I have Charlie Masters, who is a research scientist and a member of the ML team at DeepFlow. By the way, I'm getting some sort of audio feedback from the crowd. Maybe you can mute yourself while I give the talk. Would that be okay? All right, seems better now. I'm gonna get into the talk. Right, so the talk has two parts. The first talk is broadly about research in multi-agent reinforcement learning, which I have been conducting primarily with my lab back at Edinburgh University. And the second part, when I'll hand over to Charlie, will be about our recent work at DeepFlow about LLM-based multi-agent teamwork. All right, so let's start with the first part. In my research, broadly, my goal is to create autonomous agents which can accomplish tasks in complex dynamic environments. And here I'm showing you a few example applications for domains that I've actively been developing over the past few years. So on the left, you see a multi-robot warehouse application. In the center is a self-driving application. I was involved for a number of years helping to build a business in this space, which was bought by Bosch a few years ago. And then on the right, there's various multi-robot teamwork applications. So what all these applications have in common, first of all, is that there's not just a single actor, but it's actually a multi-agent system. There are multiple actors in this space, and they coexist in this shared environment, and they need to coordinate their actions in order to achieve a certain task. And secondly, what's common is that we use a technique called reinforcement learning in order to train these systems. So I guess I don't have to explain here what reinforcement learning is. Everyone will be aware. It's the idea that an agent gets to explore the environment to collect experiences, and then based on essentially trial and error, improve its behavior over time. So in this talk and this first part, I want to tell you about a very basic idea, which is experience sharing, and that's led to some really interesting, strong performance results, and it actually leads to a whole spectrum of research opportunities. Then I'll tell you about a particular application, and then we'll get into the second part of the talk. Right, so here's a paper that we published a few years back at NeurIPS. It's a really simple idea, but very impactful in terms of performance, and that's why I still like to talk about this in my talks. So here I'm showing you 4 example domains. They're various toy environments where teams need to solve a task. For example, in the second task here, this is based on a computer game called StarCraft, where we are controlling this red team, these red Marines, and they need to destroy the opponent blue team. And basically, they share the space. They have to interact and coordinate how they navigate the space and how they, for example, attack the opponent units. And importantly, this is a really difficult learning problem because first of all, it's a large combinatorial action space. There are all these actions available to the individual agents, and they need to combine their actions in certain ways in order to achieve their task. So it's a very large search space. But more importantly, it's also a highly non-stationary environment, because from the perspective of every individual agent, because everyone is learning concurrently, from an individual agent's perspective, it seems like the environment is non-stationary. It's constantly moving, so every agent has to constantly co-adapt to the other agents in the environment. And it makes it a bit difficult to track and to adapt to one another. And in addition, this is also difficult because we have what's called a sparse environment, which means that almost all of the time, the agents receive a zero, and only in few defined moments do they get a positive reward. So in this case, it's when they destroy the opponent team. So there's a long horizon in a combinatorial search space in a highly non-stationary learning environment. It's a very difficult learning problem. The main idea that we're proposing here is shared experience learning. It's really quite simple to explain. So I'll explain based on this basic task that you see in the image here. This is a 2D navigation task where there are two agents, the blue agent and the green agent. And their task is to navigate in this space. They can go up, down, left, or right, and they need to arrive at the center point location at the same point in time. Now, in the standard multi-agent RL approach, which is called independent learning, every agent learns entirely independently. So you only use your own experience and you ignore the other agent. There's no explicit representation or modeling of the other agent's existence. So for example, the blue agent only uses its blue trace of experiences, and it's ignoring what the green agent has been doing. The blue agent uses this data, computes its policy updates, and then goes into the next step in the loop. And what we're saying is, well, there's probably an opportunity for the blue agent to also benefit from the experiences of the green agent, because clearly what the green agent is doing is closely related to what the blue agent is trying to do. And so basically, we are now putting the blue agent into the green agent's perspective so that we enable it to use the green data, right? But because the green data, the green dotted line, was produced by a different policy, namely the green agent's policy, we have a distribution shift problem here. This is basically off-policy data that was produced by a different policy, and we need to correct for that distribution shift by using an importance sampling technique. Now the blue agent can use all of the data in one place to compute more robust policy gradients. And that basically is the whole idea in a nutshell. For those of you who are maybe interested in the technicalities, this is how it looks in terms of the loss function. The blue box here is the standard policy gradient applied to agent I's policy parameters or actor parameters using the observations and the actions of the same agent. And the only modification we now make is this and this bit here shown in the brown or red box. We are adding to this the exact same application of policy gradient using the same agent's parameters for the same actor, but applied to the actions and observations of the other agent, in this case, the green agent. And as I explained, we use an importance sampling ratio, which is the thing shown in the box in front here, in order to correct for the distribution shift. In this case, it's just vanilla importance sampling. You could do much more sophisticated things, of course. That is basically all we do in terms of modification. We don't use any sophisticated architectures. We don't use any sophisticated training pipelines. It's all pretty straightforward. Let's look at some results. So here's two of the toy environments that I showed you at the start. At the top is the StarCraft game, and at the bottom is a multi-robot warehouse toy environment. And the results for the StarCraft game, just to explain the axes, on the x-axis you have the environment training steps. So you get more environment data the more you go to the right. And on the y-axis you have your returns. You want to be as high as possible. There will be three different lines. The blue line is independent actor critic. This is the independent learning approach that I explained at the start. And then there's the shared network actor critic. This is the orange line, when all agents use the exact same policy model and all the data from all the agents is used to jointly train the shared model. And then there will be the green line, which is our approach. It uses the same architecture, but it uses the shared experience approach that I explained earlier. And the results look like this. You can see that the two baselines, they learn nothing. Basically, they learn, in fact, to run away. And the green agents, the green return lines, they actually successfully solve this task. And the only difference being that they share the experiences. Similar results for the warehouse task, where you can see that the two baselines are outperformed by our approach in terms of sample efficiency, but also in terms of arriving at a better local optimum when we converge. So in the paper, we show many more results with much more complicated, larger environments, and we're also comparing against much more complicated state-of-the-art algorithms at the time that we were outperforming. But I think the important question is, what is it about experience sharing that enables the learning agents to arrive at a much better local optimum? Because we're not using more data. We're also not using different data. We're just using the same data in different ways. And so we went ahead and basically studied the impact of this experience sharing. And basically what I'm showing you here is a plot that shows two blue lines, which correspond to the individual returns of two of the learning agents in one of those learning tasks. And what we often found is that the agents learn at different rates. So you can see there's this red bar here, the red horizontal bar. There's this discrepancy in the learning progression. One agent becomes proficient earlier on, and then other agents lag behind. When this happens, we find that the agents have a hard time closing this gap. Basically, the more advanced agent is essentially depriving the slower agents from catching up. And when this happens, they're not able to explore the space as effectively, and they converge to a suboptimal solution. Now, the same task, but in the green line shows you the individual returns for two of the learning agents when they do share experiences. And you can see that they learn much more efficiently initially, but also they end up in a better local joint policy. So what we found is that by the act of sharing experience, basically, they execute a uniform learning progression where basically no one is left behind. And this enables them to explore effective joint actions much more productively and learn more effectively. Here's a video that shows this in action. This is for the StarCraft task, where we are controlling the red team and we are against the blue team that is controlled by an AI agent. You can see that, first of all, our team is learning to spread out, and then there's the fire patterns are focused on the central units and the high energy assets of the opponent. You can see that our healing unit is focusing on the healing the high energy asset as well. You can see that we're quickly dominating the opponent team here. I think what's interesting is that we didn't tell the team anything about these teamwork strategies, for example, what it means to spread out and what it means to concentrate fire patterns and so on. It was all learned in this sparse, highly non-stationary learning environment. Now, I've told you about this one idea, but this is interesting to think about this in terms of a spectrum. And this is what I would like to share with you, basically. On the left, you see there's this, on the one end of the spectrum, there's no parameter sharing. This was our blue line, independent actor critic. The advantage is that agents can develop different behaviors, which is important for teamwork, but it's also very inefficient because we have a lot of parameters and a lot of policies, and learning is slower. There's no data being shared. On the right end of the spectrum, we have our full parameter sharing. This was the orange line, when there's just one model and all the data goes into that one model. It makes training very efficient, but it's not good for teamwork because in teamwork, we need the ability to differentiate behaviors, which you cannot do if they use the same model. And so you can think about these intermediate steps here. For example, the shared experience actor-critic idea that I just presented is somewhere in between the spectrum. We have a different trade-off profile. We can develop distinct behaviors, which is important, and also we can be more efficient because we do share data between the agents, but we still have a lot of parameters because they're separate policies. In another paper in ICML a few years ago, we proposed another sharing method where we enable agents to decide for themselves how to cluster agents in terms of their parameter spaces and then with whom to share their parameters. And more recently in NeurIPS this year, we have a new paper in this space where we actually train a hypernetwork that is basically jointly learning the downstream parameter spaces for the individual policies. And you can see that there's quite a space here, a spectrum of ideas you can explore, and there's obviously a lot more ideas you can explore in this space. Now, in the next bit, I want to tell you about a particular application that we built on top of this. We teamed up with a large warehouse automation company called Dematic. They operate basically everywhere in the world, and they built these high density storage solutions like the one you saw here. Basically, with them, we asked the question, well, we want to build a warehouse. And in this case, what you see here is a snapshot of a high fidelity simulator that we built with their engineering team. And in fact, this is actually from a car parts manufacturer in Germany, in a city in Germany. Basically, you have your aisles with different locations, and then you have two types of agents. There's the humans, we call them pickers, because their task is to pick items from the shelves. And then there's the robots, the AGVs. Their task is to collect the items from the human pickers and bring them back to the processing stations. You can see there's a bunch of different existing heuristics that the engineers at Dematic actually have developed for this kind of use case. And our question was, well, can we use multi-agent reinforcement learning to outperform these existing industry solutions for any given warehouse specification you give to us? let's look a little bit more at the problem and how to think about this and why it's actually difficult. So on the right, you see the same snapshot. You see there's these different components like the human pickers and the AGVs. The objective is to learn a joint policy pie, which includes policies for the individual workers, including the human pickers and the AGVs. And they need to jointly maximize, in this case, the pick rate. So the order throughput, how many orders can they process per hour? Orders are continually sampled from some unknown order distribution, which can also shift over time, for example, Christmas season. They can observe various things. For example, the pickers get to observe the locations of the agents and their order lines. Similarly, the AGVs have observations about the locations and order lines and so on. There's a very large action space, which consists of all the possible locations in the warehouse. And if you take this together, it's actually a pretty hard problem. To begin with, we have an extremely large state and action space to explore. In this case, if you only consider 20 workers and let's say 660 locations, which is what we have in this specific snapshot you see here, then we have this astronomical joint action space to explore, which is entirely infeasible for any existing reinforcement learning, single agent reinforcement learning approach. In addition, we have our sparse rewards again, which means we only get the rewards at the end. And again, we have our non-stationarity. Everyone is learning at the same time. So in our solution to this, there are quite a few things of course, we're building with the engineers, but at the high level, there's really this one core idea that I want to share. And I think this is a really neat idea that can be, that is very broadly applicable. Basically, we have this manager agent, which exists and has oversight over the teamwork. So you can imagine in the warehouse, there's a manager agent that sits at the top and gets to observe the whole space. And its task is to learn a policy that assigns goals to the individual worker agents, such as saying things like you go here, you go there, and you do this thing. At the same time, the worker agents, which are the human pickers and the AGVs, they receive those instructions from the manager, and they need to learn concurrently how to execute those goals in this physical space. And so we're using multi-agent reinforcement learning to jointly optimize this architecture, the policy for the manager and also the policies for the workers at the same time. It's a basically hierarchical task decomposition where we leave it to the agents to negotiate with one another how to decompose the task space and what it means for the manager to assign these different tasks to the different workers. In terms of evaluation, we tried this in a few different example warehouses. Again, these are actually based on real clients that Dematic was working with. For example, there's the large one we saw earlier. There's also a disjoint warehouse where there's a cold compartment that needs to be separated from a warm compartment with a narrow channel. So it creates additional navigation challenges. And here's some results in one slide. So there's a lot going on here. Let me explain what you're looking at here. So there's 4 plots corresponding to the different sized warehouses: small, medium, large, and disjoint. And then on the x-axis, you have your training episodes, and on the y-axis, you have your order lines per hour. You want to be as high as possible. So you see a bunch of different lines. First, there's the horizontal lines, which are corresponding to 2 of the existing industry heuristics that Dematic have built for this type of system. And there's no learning. They're just basically, they're just heuristics. There's no learning over time. One thing you can see here is that, first of all, we are outperforming them. So the learning curves here are the multi-agent RL approaches. And you can see that we very significantly outperform them in terms of the order lines per hour, which is great. We can operate in these different warehouse specifications. But one thing that's not immediately obvious, which is maybe even more interesting, is that if you look closely at the heuristics, you can see that sometimes one heuristic is best, and sometimes the other heuristic is better. It depends on the layout of the warehouse specification. But in our case, we don't care about this type of detail. You just give us whatever specification you have for your warehouse, and we optimize as hard as we can, basically, the performance of the joint policy in the space. So we're always better than any of these 2 existing heuristics. Here's a video that shows you this for the same snapshot that I showed you earlier. So you see that they're basically swarming out, and they're now executing the collection of these, or working through the orders as they come in. Based on this work, with Dematic, we have started a prototype that we have opened up in a test facility in Germany. And this work was also published at AROS last year. So to me, this is a nice example of how an idea from a lab transition into this industrial space where we're trying to scale it up now and make it a real product and basically have a real impact. And this is so currently running basically, and we continue to work with them on this. Now, lastly, you've heard a lot about multi-agent reinforcement learning, and of course, you're all excited about learning more about this. And we have you covered as well. So we have a brand new book, which we published with MIT Press. This is available online on the URL that you see here. You can get the PDF for free. And the book is designed to cover the whole story. So it gives you the introduction to reinforcement learning, game theory models, solution concepts, deep learning, and then there's a big chapter on multi-agent deep reinforcement learning and various practical aspects. We also released a code base developed in Python, where we have a bunch of algorithms that are ready for plug and play, and they're designed to be easy to use and easy to read, so students can quickly get involved. And if you want to teach this based on the book, we also release the lecture slides for most of the chapters, which are based on LaTeX, and you can shape them up to whatever you need for your course. So we also have some nice support for the book from various other authors and RL professors, and also very happy to say that there's a Chinese translation coming out this year as well. Right, so now this is the end of the first part about multi-agent reinforcement learning. And now I'm going to hand over to my colleague, Charlie Masters from DeepFlow, who will be telling you about a very recent piece of work that is about LLM-based multi-agent orchestration. And I'm going to mute myself, and Charlie, you can, I think, take over now.
Okay, well, thanks so much for the introduction. Just give me perhaps 5 seconds. Stefano, are you still sharing your screen?
Yes.
I can't see your slides. That's problematic.
Okay, interesting.
There we go.
What
cool. No, now I can. There we go. Thank you so much.
Now you can? Okay. All right.
Okay, so first things first, as Stefano introduced me, my name is Charlie, and I work with Stefano in our AI R&D team, where at DeepFlow, we are trying to solve a series of multi-agent, mostly LLM-based challenges. Today, I will be presenting some of our more recent work on the concept of a manager agent, where we pose the manager agent as a unifying research challenge in orchestrating human AI teams in a multi-agent setting. This has just been accepted into the conference for distributed AI this year, which will be happening next week. If anyone's in London, feel free to come. It'll be a good time. So, at a high level, this talk, I will go through briefly what DeepFlow does and how we think about multi-agent executions of real-world projects, how that necessitates the need for a manager for these complex environments. In light of that, how we pose the problem to the community and what we've contributed to solving the problem thus far. So, without more ado, yes, what is DeepFlow? So DeepFlow is a company where we build a operating system or platform for the management of work, where we plan, execute, and coordinate work at a very large scale for a range of different companies and domains. So how do we do this? On the right, you can see a screenshot of our platform where we are trying to execute a project. This is a project that we mocked up for a talk that we gave at Huawei. Thus, the project was the training of a vision action model in a decentralized manner to deploy to a series of edge devices in a fleet. So how do we think about projects? We think of project work primarily as a directed acyclic graph of tasks, where a task is an atomic unit of work, which can be assigned to an agent. An agent can be either a human or a machine worker, whose goal is to execute the task as optimally as possible. So, as Stefano talked a bit earlier on about in his in stage one of this talk, project level work often requires delegation. So both human beings and AI have a natural upper bound as to the size of task that they can take on. And it's normally quite effective to break down work into manageable steps. Similarly, in the DeepFlow platform, we do this solving a delegation problem and a refinement problem. Refinement being taking a task and breaking it down into itself a directed acyclic graph, as you can see on the right, where we've refined a series of tasks from our prior slide, which we can then go delegate to workers. Delegation being the optimal allocation of agents to tasks in an environment. So, as you can see, this gets quite complicated quite quickly. So this is an example of us refining down a workflow in the prior example, and already the cognitive burden is very heavy. So the ultimate question is, as a human being, we have to manage this process, as does every company. Can we design autonomous systems, be it a manager agent, to manage this complex workflow for us? So, in line with that, language models, as I'm sure everyone in the audience is fairly familiar, are getting highly competent at solving long-range task planning problems. So on the right, we have a plot of the average length of a task that an AI could complete extrapolated over time. I think this plot is probably about 6 months old now, because the most recent model I think on there is 3.7 sonnet. But we can see something of a exponential scaling of the length of a task that LLMs have been able to complete over time. And we are still seeing this extrapolation hold. Therefore, we're seeing that LLMs are becoming increasingly capable at solving these complex planning problems. Would they be effective in solving our manager agent challenge? So as part of this, we identify 4 key challenges, which we're going to present to you now. So the first challenge we've just touched upon is the challenge of hierarchical task decomposition. So as we break down tasks into subtasks, there's a natural trade-off where an agent cannot reliably perform a task that is too large, but the more complex the breakdown that we do, the more complex the dynamics of collaboration between different agents in our system have to be. The increased cognitive burden of the workflow or project as a whole becomes, and an increased fragmentation happens where tasks may need dynamic context management. The second challenge we bump into is the complex nature of preferences in project level work. So on the right, we have a very brief description of, for a project, we say a stakeholder is the person that work is being completed on the behalf of. And here is a visualization of a stakeholder at time t with 3 preferences, which we've scalarized, being the reduction of cost for the project, the pace of execution, and the quality of the final output. So we can then say at a time t prime, these weights may change, or even more complexly, actually, maybe new categories of preference that we never saw previously become more important or start to be considered. This means ultimately we have a multi-objective, non-stationary optimization problem of the manager agent in our environment. Contemporary methods do solve parts of this problem, but there is no one method that solves the entire problem synoptically. The third problem is a quintessential problem in the multi-agent systems literature, being ad hoc teamwork. The ad hoc teamwork problem is, in essence, that I, as a manager, will have to collaborate with agents in an environment where I have not been trained in conjunction with only partial observability into perhaps what they're capable of, what their backgrounds are, and what their general skills are. So we've got an example of this on the right, where I have, in the DeepFlow platform, taken a task and broken it down into a subtask. And then I have delegated these tasks to different agents on our platform, being them a research agent, a marketing agent, a coding agent, and myself. A manager managing this parent task would have to, based off of only maybe brief descriptions of these agents and their capabilities, reactively plan and manage this task as well as possible. This is ad hoc teaming. The fourth problem exists primarily in quite a lot of our more complex environments where there is a critical need for governance. So governance and compliance in our multi-agent systems proves to be quite challenging because real-world projects are may stipulate quite ambiguous requirements. We may have both hard and soft constraints. So for example, a hard constraint could be that the law needs to be adhered to. A soft constraint may be something like budget or a timeline. Balancing all of these, interpreting them from natural language and adapting to them over time in our heterogeneous teams proves to be quite challenging. So these are four of the problems that we've encountered and theorized as being a main barrier to the creation of autonomous manager agents. How do we solve them? So we contribute to the community what we call MAGIM, or the Manager Agent Gym, which is a high fidelity simulator for the execution of workflows. So in MAGIM, we contribute a full multi-agent coding environment to build and test manager agents. And to test the current state of frontier models in this environment, we handcraft 20 realistic workflows across a range of domains, including law, finance, programming, marketing, and etc. And we evaluate how effective different agents are at managing these complex processes. So here we have a brief visualization of a real-world agent run of, I believe, GPT-5 running on a Gen AI feature launch. And this serves as quite an effective visualization of some of the things that a manager agent might do to drive these workflows. So on the left, you can see discrete actions that a manager agent is taking and a brief description of their rationales. So it's doing things like assigning tasks to different agents, breaking tasks down into subtasks, inspecting the current running status of different tasks in a workflow, refining their descriptions and acceptance criteria, and generally driving the state of workflows through to completion. So now we move on to the results. So this is quite a complicated plot, but what we plot here is a series of measurements that we think are important to codifying the goodness of a manager agent across each of our 20 workflows. We run this for 3 baselines, be them our manager agent, where as a faithful policy, we implement a React style or chain of thought agent, an assign all baseline, which is the crosshatch plot, where what we do is we assign all tasks to a suitable agent to complete them initially, and then we perform no managerial work. So there is no reactivity to the environment. It just runs as a fixed workflow. And then finally, we have a fully random policy where the manager agent is forced to take a random discrete action, such as assigning a task to an agent, but has the freedom to decide after that what agent to assign to. So here we visualize some of those results. And if we click, I will summarize some of the key results for you. So the first key finding is in goal achievement, where as a result of the complexity of some of these real-world tasks, a chain of thought baseline manager agent, where we use GPT-5 as a faithful frontier model, often for the metric of goal achievement, which for context we measure with verifiable rules for each of our examples, fails to deliver significantly different returns on average to the random policy. And on a number of our workflows, fails to outperform even the assign all policy, which means that actually having a unsophisticated manager can be actively detrimental to the completion of a workflow. The second key result that we see is an interesting qualitative difference in how different baselines or algorithms manifest their policies. So we can see this in task delegation. So on average, our chain of thought baseline takes 47 hours in simulated wall time to complete a workflow, whereas a random policy takes 2.7 hours, which is 17.5 or so times slower. This manifests for important reasons, which we'll discuss in a second. But another interesting qualitative difference is that all agents for all the models that we've run and for all of these algorithmic baselines neglect stakeholder management. So the stakeholder, to remind you, is the person the work is being done on the behalf of. And the manager agent in MAGIM has the ability to query the stakeholder dynamically to understand their preferences for how work is done, which links back to the second challenge that we presented to you. This consistently is not performed well enough. Manager agents basically just cut and run with the completion of work, which isn't acceptable in industry. And then the third point we see is some quite interesting qualitative differences between different models in the same class of algorithm. So we run as two faithful baselines, again, GPT 4.1 and GPT 5. And not only do we see quantitative differences in the returns of things like goal achievement or the alignment to the stakeholder preferences, but we see qualitative differences in how they go about achieving these things. So GPT 4.1 is quite likely to just take the next task, which is pending to be completed, assign it to an agent which has capacity, and carry on working, basically, in that fashion. Whereas GPT-5 is much more likely to proactively plan, refine the requirements or the descriptions of different tasks, and is much more likely to break down tasks or add dependencies to a workflow, presenting some level of proactive planning description. This is interesting because obviously GPT-5 is a reasoning model that has been post-trained with reinforcement learning with verifiable rewards. And therefore, that poses quite attractive or promising results in that RL may prove effective for building manager agents with policies aligned to what we hope for. So to sum all of this up, there's some promising results, but actually the problem is quite challenging. So frontier models can complete workflow goals to some extent, but the environment is very complex and there's a series of trade-offs, and we didn't find any frontier model which can balance stakeholder management, the constraints of the environment, achieve its goals consistently, and handle basically the trade-offs between each of these things. So just to summarize a little bit, we think that we've bumped into quite a difficult challenge and we'd quite like some help solving it. So as Stefano's put up here, we're expanding the team at DeepFlow. And if you are interested in solving problems around multi-agent systems, preference alignment in post-training of models, how to solve these ad hoc teaming problems, and generally just build out really powerful environments for agents to collaborate with humans to complete work, send us a message. We'd love to hear from you. You can also see on the right, there's a QR code for the paper. Again, if you're in London, feel free to check out the conference. It'll be quite interesting. And please give MAGIM a peruse. We're building on it actively. So we've already released our second paper, which we've submitted. And we plan on actively contributing to it as our ability to solve this problem.
All right. Thank you very much, everyone, for your time. In particular, also all your PhD students, feel free to share that we're hiring and maybe take a photo or make a note of the contact. I think we maybe have a few minutes for questions.
Yes, there's probably time for a question if someone has one. So I had one question. It seems to me that you're very much working in a system where all of your agents have perfectly aligned preferences, and your manager has, in some sense, full access to all the information from every agent. Are you able to do anything where you limit the information flow from agents to the manager and still optimize with minimal information transmission?
Do you mean in the DeepFlow application here or in the other manager agent in the warehouse? Sorry, it's a bit confusing.
I was thinking more in the warehouse example.
Sorry, yeah. So it's a partially observed environment. The workers, which are the human pickers and the AGVs, they only see a part of the environment, which is basically determined by their sensing ability and other information that's provided to them, like the order line information. And the manager agent also only observes partially, but it can observe in principle more than the localized agents. Manager agents can actually learn to flow information to the workers, which could be part of their instruction, right? And the interesting thing is that we leave it to the agents to negotiate how to attach meaning to the signals that are sent by the manager agents to the different workers. So it's quite cool. But one thing we cannot really fully analyze is the basically what they ended up really learning, because these are just vectors. It's all basically black box policies, and there is this problem of explainability, interpretability that we currently, it's still open question.
Thank you. Thanks for the presentation. You mentioned that in the first example with the warehouse that you can then change all the different warehouse configurations and it still works. How do you go about achieving that?
Yeah, so basically, as I mentioned, we built this high fidelity simulator with a team of engineers at Dematic. It allows us to represent things like different types of robots and vehicle models and their kinematics, different order profiles, for example, the frequency of orders and the types of orders and quantities. We can also represent different physical layouts of the warehouses. So by being able to represent these different specifications, we can then run the training loop in multi-agent reinforcement learning on top of these specifications, which is the process that we use to produce the data or the experiences, as it's called. In addition, we can also build things on top of this after the training and the simulation loop. When the system is actually deployed in the physical space, you can continue to collect data from the deployed environment and then do fine-tuning subsequently, or even use this data to do offline reinforcement learning outside the simulator. So it's quite flexible, the setup. But the base approach gives us the flexibility because the simulator is able to represent a whole variety of physical constraints and models.
So you train from scratch on each new layout?
Yes, that is basically the base approach. Now you might be getting at a different question, which is about transfer, and that's an interesting question, right? We have explored this as well, and we're building techniques for this too to gain efficiency gains. So transferring from one learned environment to another. Clearly, it should be possible to transfer learned skills from one warehouse to the next and continue to refine them. For the particular business application here, that's not a requirement because we just need to rigorously optimize for whatever specification we are provided with. But longer term, I think it would be nice to have a system that can be deployed essentially off the shelf and quickly adapt online, right, after a few new observations. But I think that's pretty much still a big open question in multi-agent reinforcement learning as a whole, where we have a few projects going on about how to generalize learned joint policies from one teamwork task to another. It's quite complicated, but very exciting research problem.
I think we'll have to stop there for the sake of time. Let's thank Stefano and Charles again.